In an arid desert basin in Mongolia, around 30 million years ago, a very large mammal was on the lookout for food. Its preferred snack was the most succulent leaves at the tops of the highest tree branches, which it could reach with its exceedingly long neck. We call this animal Paraceratherium, and it was one of the largest land mammals to ever walk the earth. Now, today, the biggest terrestrial mammal is the African elephant. But Paraceratherium was no elephant. It was actually a kind of rhinoceros, though you probably couldn't tell by looking at it. But back in its day, rhinos came in all shapes and sizes. It arose from rhino ancestors that were a lot smaller. But Paraceratherium would take a different evolutionary path, one that would offer both the advantages and disadvantages of large size. Believe it or not, it actually became so big that it probably got close to what scientists think might be the actual upper limit for a land mammal. In other words, Paraceratherium might have gotten literally as big as a terrestrial mammal can get. So what happened to it? Well, the short answer is, it ran into some problems that were even bigger than it was. The first fossils of Paraceratherium were found in 1846 in what's now Pakistan, and more fragments were soon found at sites across Asia. But it wasn't until 1922, when more remains were discovered in Mongolia, that scientists began to really understand this animal. From the anatomy of its feet, they could tell that it was a perissodactyl, or an odd-toed ungulate that stood on 3 toes. Perissodactyls today include animals like horses, tapirs, and rhinos. But how did they figure out that this big, weird-looking thing was actually a rhino? Well, just like a walrus can still be a walrus, even if it doesn't have tusks, which was news to me, it turns out that it's not the horn that makes a rhino a rhino. Instead, it's the shape of its teeth, specifically its back teeth. Rhinos have very distinctively shaped molars. Their upper molars have a chewing surface that's kind of shaped like the Greek letter pi, while the lower molars have more of an L-shaped pattern to them. And Paraceratherium had exactly these kinds of patterns on its molars. From these early fossil discoveries, some reconstructions of Paraceratherium gave it a more rhino-like appearance. It had squat, robust legs with a short neck that stuck out parallel to the ground. But as more of these animals were uncovered, it started to look less like a modern rhino and more like some kind of cross between a rhino and a giraffe and an elephant. Like a giraffe, it had a really long neck, about 2 to 2.5 meters long, that it likely held at an angle. And like modern elephants, and even sauropod dinosaurs, it had thick, column-like legs to support its heavy build. But the proportions of those legs were very different. In elephants and sauropods, as those animals got larger throughout their evolution, their humerus and femur grew longer, while the other bones in their forelimbs, hind limbs, and feet became shorter, more compressed, or even fused together. But in Paraceratherium, the limbs didn't look like this. Its humerus and femur were shorter, and its lower limb bones were longer, more like the legs of other ungulates. And these proportions were similar to those of its ancestors, which were better built for speed. One of these earliest rhino ancestors was Hyrachiris, a lightly built herbivore from the Eocene epoch that looked kind of like a tapir. And like Paraceratherium and modern rhinos, it had those characteristic pie-shaped and L-shaped molars. From Hyrachiris would come 3 families of rhinos: the group that would lead to our modern horned rhinos, a now extinct amphibious hippo-like group, and the group that would eventually lead to Paraceratherium. Early members of this group weren't really big, but they were adapted for running, with long legs like those we see in Paraceratherium. Take, for example, Papaceris from about 50 million years ago in China. It was around the size of a dog and used its long legs to escape predators. But it wouldn't be long before these running rhinos started to get bigger. For example, Juxia from the late Eocene epoch of China was about the size of a horse. It also had a longer neck, probably to help it browse in places other mammals couldn't reach. And by the start of the Oligocene epoch, about 35 million years ago, giants like Paraceratherium measured a whopping 4 to 6 meters tall at the shoulder and around 7.5 meters long. I didn't know he was there. And with its long neck, it was likely the tallest land mammal that ever lived, with a head height about 6 to 9 meters off the ground. So how does a mammal that big just be that big? Well, some experts think that Paraceratherium was probably close to the maximum weight that a land mammal could reach. It weighed between 10 to 15 metric tons, with the largest possibly reaching up to 20 tons. Interesting thing is, that weight limit might not exist because of biomechanics, but because of basic biology, specifically reproduction. That's because typically, the larger a placental land mammal is, the longer its pregnancies are. So for example, the African elephant, the largest placental land mammal today by mass, has a gestation period of up to 2 years. So imagine how long a female Paraceratherium, which is probably twice as heavy, would have to carry her offspring. That would require a lot of energy and nutrients for both the mother and the baby, which, like elephants, needed to grow quickly at first to avoid predators. So why did these animals get so massive in the first place? Why go from the dog-sized Papaceris to the enormous Paraceratherium? Well, one reason that you've heard me mention before is just that being huge usually makes it harder for predators to take you down. Another reason is that larger animals were able to access foods that are out of reach for smaller animals. Based on the size, microwear patterns, and chemical analysis of their teeth, we know Paraceratherium mainly ate leaves. And with their long necks, they could reach plenty of leaves from the tops of the trees, like giraffes do today. Researchers also think that they had the same type of digestive tract as modern rhinos, which means they probably didn't get very much nutrition from their diet. So they likely needed to eat huge amounts of plant material to get enough nutrients, which required a large gut to process all that food. And fortunately, they could probably travel pretty far to sustain their giant bodies. For example, African elephants, which need roughly 140 kilograms of food every day, are capable of traveling around 32 kilometers in a day and have home ranges between 750 and 1,500 square kilometers. And this is possible because their long legs give them a long stride, longer than any other animal today. Paraceratherium might have had an even longer stride with an even larger range. And this would have been a big advantage, especially considering the changes to the climate that were going on. Around the start of the Oligocene epoch, about 33 million years ago, Earth began to cool, and glaciers in Antarctica started growing faster. This cooling trend continued into the early Miocene epoch and expanded areas of semi-arid climate with more shrublands, dunes, and savannas, gradually replacing the tall trees that these animals preferred. But these climate changes actually didn't seem to have much of an effect on Paraceratherium, at least not directly. They were probably already used to harsh environments. But there was another unexpected factor that may have led to their extinction: the arrival from Africa of gomphotheres, some ancient relatives of elephants. Paraceratherium probably didn't compete with these newcomers directly. Instead, the gomphotheres helped accelerate the disappearance of the rhino's habitat. We know that as modern elephants graze, they can push down trees and greatly change the environment around them, turning woodlands into grasslands. Gomphotheres likely did the same thing, putting additional pressure on Paraceratherium as it left even less food for them to browse on. And this stress could have also made these ancient rhinos more vulnerable to disease and droughts. The start of the Miocene marked the end of these largest of the rhinos, with only their smaller cousins left behind. And it set the stage for the rise of a different group to take the crown. Those elephant relatives soon became the largest mammals on land, diversifying into niches previously occupied by the giant rhinos. And some of them reached enormous sizes too. In fact, some species, like Paleoloxodon, probably got heavier than Paraceratherium, and maybe even taller at the shoulder. But Paraceratherium still reigns supreme as the tallest mammal that ever was. Extra-large animals need a particular combination of climate, resources, and space to exist. And these circumstances come and go as the planet warms and cools, and as new groups diversify and migrate across continents. But if modern rhinos and elephants, and even the whales that we know today, are any indication, it looks like getting big is a strategy that will never go out of style. Okay, now, do you want more Eons content? Then be sure to follow Eons on social media. You can find us on Instagram, Twitter, and Facebook. And you can join me on Instagram at Western Digs. Largest high fives ever, thank you, Callie, to this month's Eontologists: Sean Dennis, Jake Hart, Annie and Eric Higgins, John Davison-Ing, and Patrick Seifert. Become an Eonite by supporting us at patreon.com/eons. And remember, Eonites get perks, like submitting a joke for us to read. This week's is from Stephen O'Leary, and I've not read it before, so brace yourselves. Evolution gave the primates the opposable thumbs up. Why? And as always, thank you for joining me in the Konstantin Haase studio. If you like what we do here, subscribe at youtube.com/eons.